הוא ביטל את ההרצאת פייתון.
נכון, אבל יש לנו תרגול לפני, אבל גם ככה לא אכפת לך מהתרגול.
אני מספיק לי זאתי, אנחנו מצחקקים, נהנים, ויש לנו דופקת לנו עיניים.
Morning, בוקר טוב. All right, so we started to treat the solid models, and we described the Einstein model. For solids, which was kind of a mixed picture, right? Or mixed success. The assumptions of Einstein, I will remind you, is that we have a three-dimensional solid. In this three dimension, there are particles that are somehow quenched to their positions, and the description of so those are our atoms, and the motion of those atoms is described by harmonic oscillations in the x direction, y direction, and the z direction. So in total we have n particles, which means that we have 3n degrees of motion. Einstein solved it using this assumption. Okay, so remember, in order to solve anything in statistical physics, okay, in order to solve anything in statistical physics, we need two assumptions. We need that the energy should be an additive function of some entities. Okay, this is step number one. Step number two is that the energy, or this additive function, should be an additive of some entities, addition or sum of entities that are completely independent. So Einstein basically pushed those two assumptions inside his model. We have 3n particles, they are completely independent, so the total energy is just a sum of the energies of all the different particles, right? And since they're independent, all those summands are independent, that's it. Okay? So factorization trick immediately applies. This is how you can compute the partition function for one single particle, right? And by using this, using factorization, you have the total partition function of everything. Thanks. But, and there is a but, we know from experiment how the heat capacity divided by 3n is behaving as a function of temperature. And the behavior is that it, of course, converges to 0, all right? And for high enough temperatures, it converges to a constant, and this constant was 3K Boltzmann. Okay. 3K Boltzmann. Einstein idea, okay, Einstein behavior, was, well, yes, we indeed obtain this behavior. So the red one was true, the blue one was Einstein, so they converge and they describe exactly the same behavior for high enough temperatures, but for low enough temperatures, Einstein model was converging to 0 extremely fast, so too fast. Okay, so this guy, or the experiments, show as t to the power 3. Okay, an Einstein model showed as e to the power minus 1 over k Boltzmann t. And what we had over here, it was h bar omega. So extremely fast. The exponential convergence when we have 1 over t is much faster than the parallel convergence. So something went wrong. Now, the expectation that it would work is a little bit naive because we threw away huge number of interactions, right? Think about it. We said that a solid is basically a sum of harmonic oscillators. And somehow, miraculously, it still works for high enough temperatures. We'll explain why it actually works. Okay? But it of course fails because the materials are not just non-interacting harmonic oscillators. Right? So this is the first attempt. Right? So science usually works like that. You try something, you see where it succeeds, you see where it fails, and then you try again when you incorporate some new additional information into your model. So the next step to understand the solids and the behavior of the heat capacity, which is universal. It's not that they found one specific material that behaves like this. Right? Now, the interesting part that almost any solid, or majority of the solids, have exactly the same behavior. Convergence to a constant and t to the power 3. So this is why you actually need to solve this problem. Because the universality, the general application of this t to the power 3 for low temperatures says something, well, there's laws, universal laws, general laws, and this is all what physics is about, right? Something that it's not applied only in this cup of tea, something that's applied everywhere. So the next step is Debye. So, Debye was a scientist, not as known as Einstein, of course, but he worked on the same problem a couple of years after Einstein. And the understanding goes as follows. So, indeed, we look on a solid, and we can try, right? We can try and look on it. As indeed as a bunch of n particles that somehow sit on a lattice and they somehow interact with each other, but we don't start at the beginning from this assumption, let's throw away all the correlations or the dependencies of all the different particles out of the window from start. Let's try and work with the problem as it is. Okay, and what I mean by work with the problem as it is, so we have still 3n particles, but the particles are interacting. And this is crucial. So first place, particles are not interacting. Einstein started with this. Debye said, well, let's start with interactions, not throw away those interactions immediately. So if we start with interactions, we still in some classical domain, let's write a Hamiltonian. Although we can look on the Hamiltonian also in quantum domain, but let's write our Hamiltonian. So what is this our Hamiltonian is? Hamiltonian is, as always, it's kinetic energy and potential energy. There's nothing more than 2. Okay, so we have Hamiltonian, and let's assume that for simplicity it can be modified later, it doesn't really matter. Well, for simplicity, let's assume that all those particles are identical, meaning they have exactly the same mass. It can be modified later, it actually doesn't matter at all. So we have 1/2 m, a summation over I, summation over j, x I j dot to the second power. So I, number of particles. It goes from 1 to n. J is the different coordinates and each of the different particles, right? So it has an x coordinate, a y coordinate, and a z coordinate. So J goes from 1 to 3. Okay? This is the kinetic energy. Kinetic energy. what else do we have? We have a potential energy. Now, Einstein said, well, the potential energy is just a bunch of harmonic oscillator. Let's write it down from start. Debye said, well, no. So we have some potential energy which depends on everything, right? Everything. So we have to write it down as x11 and x12 and x13, right? And x21 and x22, etc., etc. And we'll continue this extremely long vector of x's, which actually have 3n entries, okay? And n is on the order of the Avogadro number. Okay? But we continue this to x and n. Okay? And this is the potential energy. All right, so we succeeded writing everything down. The problem with this is that you cannot do anything because this is a very complicated function of huge number of different coordinates. You have 3n coordinates, and you're stuck, right? So this is why Einstein said, oh, let's start with the harmonic potential, harmonic oscillators. You need to do something, and this something is a physical assumption. So what usually happens? What usually happens is that the system is in equilibrium, and it sits on a specific point, right? There is a minimal energy of this guy and this guy. There is a minimal energy. The system prefers to be in the minimal energy, right? But it has some fluctuations. So it fluctuates a little bit to the right and a little bit to the left in this 3n dimensional space, okay? So, and the fluctuation shouldn't be extremely large, because otherwise we will see, modifications of the matter as a function of time. But we see some, usually take a material, a solid, you look on the marker, nothing happens to the marker. Okay, so fluctuation should be not extremely large. So what we will do, we'll expand this function in a Taylor series, right? Why not? Around some specific minimum. Okay, so there is a minima. Let's call it x0 vector, which is x11, 0, x11, 0, x12, 0. This is 3. X and 3, 0, which is minimum or the position of minimal energy. And we'll expand our potential around this minimum in a Taylor series. That's all. Now, you don't really need to expand anything over here, right? You don't need to expand anything over here. You need just to expand this function. Now, as a good physicist, you always expand till something interesting happens, right? Because, well, Taylor series, sometimes it's convergent, sometimes it's diverging, but Taylor series can, in most cases, unless the function, something funky happened to the same function, you always can replace a function by a Taylor series. But in a lot of cases, it's specifically when you have such a long vector inside the function, it's usually useless, so you need to be careful with your expansion. So what do? So you say, well, I take this u of vector x, right? U of vector x, and x is a general thing, which is x is x1, 1, x1, 2, till x and 3. Okay, so this is the general position that describes the whole system. We use each and single position of each and single particle in the all three-dimensional space. And we say, well, this is approximately, it is u of x, how have we written it? X0 vector, plus a sum of I goes from 1 to 3n of du to dxi computed at x equals to x0. Okay. multiplied by some x minus x0. Okay, so this is the first expansion. Now, notice that here, I start to count, instead of counting, oh, this is the first particle, this is the second particle, this is the third, this is still the first particle, I stop and carry. I'm looking on my coordinates as if I have 3n degrees of motion. I don't care how they interact, all those degrees of motion. I'm starting to forget that they all describe different particles. So here, this is degree of motion of the this is the third degree of motion of the first particle. I don't care. For me, it's going to be the third degree of motion. And this is the first degree of motion of the second particle. I don't care. I will call it the fourth degree of motion. So in total, I have x1 till x3n. Okay. Great. Now, usually I expand to, this is a constant. Right? This is a constant. I don't care about constants. And there's something else which is going to depend on the small fluctuations around the minimum. Should I stop over here? What do you think?
No.
Why not?
It's 0.
Great, great. It is 0. I'm expanding around a minimum. So x0 is the point of minimal energy. What energy? Potential energy, right? I'm expanding around the minimal potential, the 0 potential energy. So this guy is 0. I don't care about this guy. Equals 0, right? All right. Constant is never enough. Oh no, never say never. But constant is usually not enough. So especially here. So we are going to expand to the next term. And what is the next term? Plus I goes from 1 to 3n. Plus j goes from 1 to 3n. 1/2 du dxi dxj, right? Computed at x equals to x0. All right, 0 over here. And on top of that, what we have over here, so it is some specific formation, right? So it is xi minus x0 I, xj minus xj0. So this is a quadratic form. Usually when you have a function of a single variable, so you just have a square over here. But because you expand according to many variables, there is a lot of mixed terms, right? The majority of the terms are actually mixed. And you have plus something, and you don't care about this something.
Why?
Why not? The answer is you always try to include something which is not 0, not a constant, okay, and forget about all the additional effects because they are going to complicate your calculation. And if you're going to succeed with minimal assumptions, then you're good. Okay? You always try to succeed with minimal assumptions. You need to assume as little as possible. Okay? You need to include as minimal amount of information as possible. Otherwise, it's going to be more and more complicated. That's it.
But why you decide to take only the mixed terms?
No. There's also not also mixed. There are different terms. But the majority, because of the double sum, the majority of terms are going to be mixed. Okay?
How can unmixed term?
They're going to be, when I equals to j, this is not a mixed term.
Oh.
Okay? And you have a double sum because of the, and due to this double sum, you have majority of the terms are going to be mixed.
Okay.
Right? Okay, so let's write it down. Write it down. This and the kinetic energy in a more matrix form, right? So I don't want to carry on all the summations, not in the potential energy, not in the kinetic energy. I want to write it down much more neatly. So what I'm going to do. So I'm going to say the following thing. Let's do that xi plus xi0 plus xi plus xi. Okay? 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 Xi plus xi0 plus xi minus, it is going to be xi. Okay. Now, out of this, I know that xi equals to xi plus xi0. So this is the value of the coordinate xi at minima. This is the fluctuation around the minima. Okay. Now, I'll need those guys in this form, and I need those guys in the kinetic energy form. Okay. Now, in the kinetic energy, I have dot, so derivatives, and I know that xi dot equals to xi dot. So all those sums I'm going to replace by what? By multiplication of vectors. Let's take care of the kinetic energy first, and then of the potential energy. So the kinetic energy, we have multiplications of different xij's, etc., etc. So what is the multiplication of different parts? I have 1/2, so the energy is 1/2 m, and here I write xi vector multiplied by xi vector transpose. Okay. Much more neatly than to write all those sums, a double sum. It's easier. It's easier to write it as it is. Okay, just multiplication of two vectors. Remember, I'm still assuming that all the particles are identical. They have exactly the same mass. We can modify it that the masses are different. Okay, and what happens with the potential energy? I'm taking only the potential energy up to the second order expansion. So I have here U0, which is a constant, right? It's computed at the minimum of the potential energy. And instead of all of those summations, I write it down as psi, a matrix A, okay, and psi transpose. Okay, that's it. You see all those terms, xi minus x0, which are xi's over here and over here. Okay, we don't need a vector over here. Right, so what is this exactly, this function? So the multiplication, so the mixed terms are coming from multiplication of a vector, okay, a row vector, a matrix, and a column vector. And the entrances of Aij are simply 1/2 du d xi d xij computed at minimum. Okay. Much more neat form, okay, for the total energy. Okay. Now, this is some sort of a quadratic form, right? It's a quadratic form. What I mean by quadratic, I have multiplications of xi I and xi transpose, and here I have a lot of mixed terms, and what I want to do is to modify somehow this function into a function that will be function without all different mixed terms. That's it.
You have to put a dot in the kinetic energy?
I have to put a dot in the kinetic energy, of course. Thanks. All right, so what are we going to do? This is our Hamiltonian, or the energy. Let's write it as a Hamiltonian. We still have not the energy, but Hamiltonian. And you have written it in a quadratic form. So we now want to diagonalize it. That's it. That's what we're going to do. We're going to diagonalize our Hamiltonian over there. All right, so how we do it? So first of all, A is a symmetric function. A is symmetric. If it's a symmetric, there is a theorem in linear algebra that you once been taught, and A is D S transpose, D diagonal matrix and S matrix constructed of eigenvectors of A. Okay. So this is the representation that I want to use. All right, so our Hamiltonian becomes 1/2 m xi dot transpose plus u0 plus what I have xi. Instead of A, I'm writing S d S transpose xi transpose. Okay. Now I have 1/2 m xi dot transpose plus u0 plus xi s d, and instead of writing S transpose xi transpose, I'm writing it as xi s transpose. Okay. So we have this guy, D is diagonal, xi S transpose. So we need to introduce another modification in the kinetic energy. Now what we know the following thing. First of all, we know that S minus 1 equals to I. Okay? Now moreover, because S constructed of eigenvectors of A and A is symmetric, S minus 1 equals to S transpose. Okay. So we know that S transpose equals to I. Okay, so I'm writing down this as 1/2 m xi I xi dot transpose dot over here plus u0, a constant, plus xi s d xi s transpose. Okay, instead of I, I'm writing as 1/2 m xi s transpose xi dot transpose plus u0 plus xi s d xi s transpose. Okay, and finally I'm having 1/2 m xi dot s transform xi s transform dot transform. It is like xi s transform dot, right, plus u0 plus xi s d xi s transform. Okay, what we succeeded in doing. Let's call this vector Cs, because it's a vector multiplied by a matrix, so it's a vector. Call it Z. Cs. Okay? It's just a matrix, just a vector. So, Hamiltonian is 1/2 m z dot transpose plus u0, which is a constant that I don't care about constants when I'm talking about energy, because it's always defined up to a specific level, plus z d z transpose. Now remember, this is crucial, D is diagonal. Now if I'm writing it down, very nice, all those vectors, but eventually what I've got, let's write everything, so I do it crystal clear, with sums. I have the following. 1/2 m, a summation I goes from 1 to 3n of z I dot squared. This is the kinetic energy, multiplication of two vectors, just one single sum, plus, now here, due to the diagonal function of property of D, what I have, plus I goes from 1 to 3n, zi d I zi squared. It's a single sum, not a double sum. So remember you asked me, oh, what about these mixed terms? And I said, the majority of them are mixed terms. Whatever we've done, eventually, we diagonalized everything. And this diagonalization means that we can write down the full Hamiltonian, of course expanded around the minima of the potential energy, as a bunch of what? As a bunch, so what was this? So this is kinetic energy. Kinetic energy. This is potential energy. This is potential energy of what? How it looks?
Virtual Hamiltonian of a virtual particle.
No. Forget about virtual particle for a second. If I'm writing down, let's take 1z. Just 1z. z1. Okay, so what I have? 1/2 m z1 dot squared plus d1 1. Okay, so let's call it multiplied by z squared.
I like harmonic.
Harmonic oscillator. So we started by claiming, oh, you're Einstein, you're fool, what you have done, you neglected everything, right? We will do better, said Professor Debye. He expanded and expanded and expanded, and he also got a bunch of harmonic oscillators, which are independent, right? They don't care about each other. Z1 does not care about Z2. There are no mixed terms. When I say that they are affecting each other, is when the Hamiltonian depends on multiplication of Z1 and Z2 or Z3 and Z75, right? Then they affect each other. But when they are written as a single sum, all the different ZIs do not affect each other, right? So we have a bunch of harmonic oscillators, and now to your virtual particles. What are those Z's? Okay, I remind you, Z's is this guy. Okay. What is Z? Is it the position of a single particle? It's not a position of a single particle. So Einstein did something. The assumption about harmonic oscillators is actually okay, right? Nothing bad about it. It's just taking fluctuations about the minimal value of potential energy. It's fine. Okay? But there are two buts in this game. First of all, those are not positions of single particles. So Z, right? Vector is the fluctuations around the minimum. So what do you have to do? You have to find the different positions of all the different particles, okay? Of all the different particles, somehow, okay? At a minimum, which is a really hard thing to do. This is he, right? And around this minima, you have to take fluctuations. Moreover, you have to take this function a, remind you, a is 1/2 du dxi aij dxj. Okay, so you have to take this matrix, which is enormous and huge, right? Find all the different entrances to this function, to this matrix, which is enormous, and S is constructed by eigenvectors of this matrix A. So think about it. You have a matrix which have a Avogadro number of rows, a Avogadro number of columns, and you have to diagonalize it. Okay? And then after you diagonalize it, right, you get the matrix, somehow you get the eigenvectors, and then from those eigenvectors, good luck with doing that, you construct a matrix S, and you multiply this by that, and this is where you're getting all the different positions of your particles. That's no position of a particle, but because no particle is sitting in a specific Z1 or Z2 or Z3, right? It's a mixture, a linear mixture, because those just multiplications of different positions with different numbers. So all the different Z's are not a specific position in one and single particle. It's a mixture of a lot of different positions of different particles. Remember what I told you, that whenever we would try to do, it to invent different representations. So what Debye is telling us is, yes, the harmonic oscillator picture, it's fine, but it does not describe single particles. It describes something else. Those Z's, okay? So Z's, they have a name. They are related to virtual, not exactly virtual particles, but we'll call them effective particles, and Z's, phonons. Okay? Those are the particles that we are looking at. They're not real particles. They're not a specific particle that's sitting at Z1. Nothing sits there, because it's a linear mixture of different positions of Avogadro number of different particles. Nothing sits in Z1 or Z2 and Z3 or Z4. Nothing. But, when you use this representation, mathematical representation, you can describe everything as a bunch of non-interacting oscillators. So this is but number 1, which is important. You say, well, okay, not different particles, different phonons. I don't care how you call them. From now on, the description is exactly the same as Einstein. And this is the second but. What is the second but? Yeah. Remember what Einstein said? Einstein said everything was simple. Let's forget about everything. All the different harmonic oscillators are identical, perfectly identical, and they have exactly the same omegas, exactly the same frequencies. When you do it properly, and I'm sure that Einstein did it properly and decided to do, to continue with his assumptions. When you do this properly, is dii different for each zi. אתם מפריעות לי? תהיו בשקט בבקשה. השיעור ייגמר בערך ב10, רבע דקה, טוב? Okay. 2 assumptions that are broken. 1, not real particles, phonons. The other one is different DIs. So, yes, bunch of oscillators, not particles, oscillators, call them phonons. B, those are different DIs, right? So the particles are not exactly the same. They're not exactly the same. What it means for us. So the moment that you have written this as a bunch of harmonic oscillators, we can proceed as Einstein. But we can forget about that these are not real particles, they are phonons, but we cannot forget that all the different ZDIs are different. Okay. So I write it down in a slightly different form. Instead of di, okay, I will write my Newtonian. U0, absolutely not important, right? Energy is always defined up to a specific constant, so U0 is absolutely not important. Plus m, a summation I goes from 1 to infinity, not infinity, I'm sorry, 3n. And here I have 1/2 zi dot squared plus wi squared zi squared. Okay. Now it's a perfect description of a bunch of harmonic oscillators. Instead of saying that harmonic oscillators, I call them phonons. Okay, so what is the next step? We check. A, is our Hamiltonian is an additive function of different constituents? Yes, it is. Assumption number 1, confirmed. Assumption number 2, are all the different constituents independent from each other? Yes, they are. This is just a bunch of different phonons. They do not affect each other. How do we know? Because there are no mixed terms. Great. So what do you know? The factorization applies, right? Now in Einstein, the factorization was because they were all identical, absolutely identical. You take Z1 up to the 3n factor. Okay? In our case, it's not true because each single particle has a different omega. And therefore, by Z is Z1, or let's call it ZW1, ZW2, ZW3, ZW3n. You have to compute all the partition functions of all the different particles with different omegas. And the question still stands. What are DIs? What are the different omegas? Right? So we don't know what is this guy. What are those guys? It's very nice that you, Debye, managed to write it down. Okay. Why it's important? Why it's important? Because, great, we compute the partition function, we have a factorization, right? We even can use the Einstein trick to find what and each different Z omega I is. But in order to follow, right, for example, to compute the heat capacity, remember what is F? Is minus 1 over B log of Z. It always applies. So F is minus 1 over beta. It is multiplication. So it's going to be a summation. I goes from 1 to 3n of log of Z omega I. I need to know all the different omega i's in order to compute this sum. Okay. And the idea of Debye up to this point is actually very simple. And the true big step of Debye is to say the following. I don't know what all the different omega's i's are. I have absolutely no idea what they are. Why? Because there is not a chance in the world that somebody will manage to diagonalize 3n by 3n, where n is Avogadro number of particles, a matrix, and to find the eigenvectors of this matrix. Even not with a quantum computer. Okay? There is no way that you can do it. Absolutely no way. Okay, so what can I do? I can say the following. So look, let's make the following assumption. So we look on the energetic spectrum of everything. Usually, all the different omega i's, what they describe, different particles, effective particles, different phonons. But what are those phonons? Those phonons are harmonic oscillators. Those harmonic oscillators describe what? They describe standing waves inside a material, right? So what kind of waves can I have? So all the different omega i's, or DI's, are all the different k vectors, right, that can live inside a medium. So if you look on this from the energetic perspective, you're saying, oh, I have energies, and the energies are, well, in quantum mechanics, they are somehow discrete. But if they're discrete, but the spectrum is very dense, okay? If everything is extremely, 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 extremely dense, okay? Therefore, if the energies are very, very extremely dense, I can also say, well, all the different omega i's are also somehow very, 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 very dense. Okay? I don't have a discrete perspective. I don't want to go into discretization and summation. I will do the following. If omega's i's are dense enough, what I can do is to make out of this, instead of a sum, I'll have to do what? An integral. So I have to integrate over something. Well, I know that I'll have to start with a boundary 0. I don't have omega which is less than 0. I don't know up to where I have to integrate. This is 3n, not exactly 3u. Okay, here I will have still log of z of omega I. Here I would have d omega I, right? Let's forget about I. But it's not that you just replace this by this, right? You need also some notion of how dense your states are, how dense the omegas are. So you need density function, d omega I, density function. Okay? You need the density function. And what we're going to talk about Wednesday, because tomorrow you have a quiz, Wednesday we're going to talk how to find this density function, what are the great assumptions of Debye made in order to find it, what is the upper limit of this integral, okay, and why it actually works, okay? So I will see you all tomorrow during the quiz, and we'll continue this lecture on Wednesday morning. Thank you very much. אני אשלח הודעה ספציפית עם רשימת שמות מי יושב איפה. הבוחן יתקיים. The quiz is going to be in this classroom and in 301. The exact list of who is sitting where we are going to publish today or tomorrow morning. Quiz is around 1 hour, and whoever is have a time extension according to lambda is going to sit in this room. This I'm going to this I can say up front. כן. אני מבין את הבעיה. אני מבין לגמרי את הבעיה, אבל אין לי פתרון. אין לי פתרון. כאילו, אם היה עוד מתרגם שהיה יכול להיות פה, כן, אז הייתי יכול להסתובב וגם להגיע לכם, אבל אין פה. אני מבין את הבעייתיות, אבל אין לי את דרך לפתור את זה. גם אם אתה תלך עכשיו למדור התאמות, כן, והם יארגנו לך לשבת ב-410 בדרך כלל, נכון? אני לא אצליח להגיע לשם תוך שעה. במבחן אני מצליח, כן, אני לוקח לי זמן לענות, ואז אני הולך ללכם. לשם, אבל אני לא אספיק לעשות את זה פה. אולי, כן, שזה אפשר לעשות, יגיע אחרי שהבוחן יסתיים, אם לרובכם יש איזושהי הערכת זמן, לא לכולם דרך אגב, אבל מי שיגמר הזמן שלו עדיין יישאר, יגיע בהערכת זמן מישהו ויענה של השאלות, אבל מעבר לזה אין כל כך פתרון לזה. ברגע שהבוחן הוא מוגבל לשעה, אתם מתפקים בעבוד כאלה? לא. רגע, אתם מפריעים פה למרצה הבאה, סליחה. עד מיקרו קנוני כולל. עד סדר מיקרו קנוני כולל. בסדר? מה שסיימנו ללמוד, לא בשבוע שעבר, אלא לפני שבועיים. יום רביעי לפני שבועיים נגמרה הרצאה, לא יודע אם נמשך. עד מיקרו קנוני כולל, אני אישי. עד מיקרו קנוני כולל. כן, כן, אבל רגע, אני רוצה לבדוק את הלוח, אנחנו נצא כדי שלא נפריע, ואני אענה לכם בחוץ על כל מה שאתם רוצים.
לא, השאלה שלי זה קצרה, כי...
כן, כן.
האם פרסמת כבר את ה... שלחת לכם מייל לרשימת כיתות?
לא, 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 אני אעשה את זה או היום בערב או מחר בבוקר. בסדר? כי לוקח לי... כי המערכת קצת מפקששת כשהיא מוציאה כל מיני...
לא, לא, אולי אני פספסתי.
לא, 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 התשובה היא שעוד לא פרסמתי, אני אפרסם.
אוקיי, תודה.
בבקשה. אין בעיה. טוב.
המחשב מסגרת איתו? אני לא, אני שואלה.
יש משהו שיותר קל לשיעור, אני מאוד אוהבת כתיבה
זה עוזר לך, לא מעיד.
זה יותר יועיל ממני שיכולים לכתוב דיקטטור. אז אני עושה את הפרנסה.
וואו, תקשיבי, אבל זה היה חשוב. אם הייתי עושה את זה היה... אני כבר 3 ימים. תקשיבי, אז יש לי 25
אני
פעם הבאה שתהיה משהו. שילמתי 4 לא, אני בסדר, חדה? נו, ספר מה אתה מסתדר?
אין שינוי.
אין שינוי, אבל אמרת שבלבש פשוט...
יותר נורמלי בהמשך הראשון.
למה לי עליי?
זה יותר נורמלי מהראשון, אבל אין הרבה שינוי.
לא התקבל. מה אתה אמרתי? שמה?
אני די חי לבד בדירה עם עוד.
אולי אתה לא מרגישים ככה. אני לא רוצה להיות
אז הוא דירת יחיד, מה קרה?
גם אמרתי רבים לוקח עליי קשה.
אני יודע.
כאילו זה קשה.
יש שיפור, לא בעיה.
גם אין לנו...
יש שינוי, לא בעיה.
אבל אני לוקח את זה אולי
לא יחליט,
מה העניינים? כן.